All right, now it's on. At least we'll have some of it. Okay, I'm sorry if you're turning on the recording right now. I forgot to record the first part of the class, but at least you can get the last part. All right, let's go back to this idea now of sympatric speciation, or excuse me, allopatric speciation when an organism is spreading out through the environment. So in other words, a river doesn't form between you, but as these organisms move out, maybe they come across a mountain range. This is a really good example. The North American salamander, Encentina enscholtzii, is an example of what we call a ring species. Let me show you what we mean by that. Initially, the population of this salamander was found up by Oregon, okay, where you see in the purple there. Through time, the population of these salamanders grew larger, and they began to move out into different habitats in different areas. And as they moved south, they came across a range of mountains inland of California, the Sierra Nevada mountains, Sierra Nevada. Anyway, there's a mountain range there. Some of the salamanders went to the west side of the mountain range, and some went to the right, and they split apart. So at the top, the coastal and the island populations diverge. All right, so we get a coastal population, and we get an inland. That shouldn't say island. That should say inland. Excuse me. There's another one of those mistakes. I've been using this slide for years, and I just noticed that should say inland, not island. All right, as we move about halfway down, so we're in this area about right here, the coastal and the inland populations occasionally come into contact with one another. They occasionally interbreed, and when they do, they produce fertile hybrids. Okay, so the yellow-bellied coastal population and the Sierra Nevada inland population, these two organisms right here. If they were to meet somewhere in the middle there, they would produce fertile hybrids. So let me ask you a question. Does that mean the yellow-eyed and the Sierra Nevada are two separate species? Or are they one? Based on that evidence there, producing fertile offsprings. They make fertile offspring. Go back to your definition. What makes a species a species? These guys are producing fertile hybrids, fertile offspring. So think again. If you're producing fertile offspring, are you one? Are you the same species or different species? Never mind all the exceptions that we talked about with the horse and the donkey, but in general. Yeah, since they can produce fertile hybrids, they're the same species. All right, now, continue a little bit further down south around the southern end of the mountain. Once you get down near LA, San Diego, in that region, the Sierra Nevada mountains begin to thin out, and the salamanders now, especially the Monterey coastal populations and the yellow-blotched and the lard-blotched inland populations, when they come back together in areas that what we call I'm back. I don't know what happened there. Just dropped me off. I'm back. Sorry about that. Okay, so when they come back together at the bottom in the blue, in areas of coincident ranges, no hybridization occurs. In other words, the species stay separate. They don't mate with each other, or the populations, let's call them here. So down here at the bottom, in the middle, you told me that they are the same species here because of the fact that they produce fertile hybrids. And down below, we say that no hybridization occurs. So what has happened down here? Are these different species or the same species? All right, so these guys don't produce fertile hybrids down here. So that makes them the same species or a different species? Different species. Now notice once again that this is an example of allopatric speciation. It's a geographic barrier, but we throw in the other factor of time, if you will, right? The time, thousands or hundreds of thousands or millions of years. I don't know much about North American salamander distribution as far as how long it took, but the time that it's taken for these organisms to move down on each side of those mountains, right? Once they get about to the middle, they haven't been separated that long, relatively speaking, so they can produce those fertile hybrids. But as we continue further south, they continue to change. They continue to become different species, different organisms, until eventually they're two separate species down there. We call it North American salamander a ring species because it rings around the mountain, and that depends, and that affects whether we have the fertile hybrids or different as we move to the southern end. All right, questions on that? Okay, I got one more thing I want to talk about in this chapter. We're at 3 o'clock. Okay, I might get into chapter 25 today. We'll have to see. We'll see where we are here. You remember that I talked to you about Darwin and the Cambrian explosion. The Cambrian explosion is an event that occurred in the fossil record about 520 million years ago, and we call it an explosion because in a very short period of time, about 20 million years, and that's pretty fast in terms of the life on Earth, folks. In about 20 million years, all the major modern orders of animals arose. Before the Cambrian explosion, there were jellyfish and sponges, relatively simple critters. After the Cambrian explosion, we had insects, we had worms, we had all the other species, all the other different groups of animals that we're going to talk about. And it appeared that they arose out of the fossil record just all at once. Now that caused Darwin lots of problems because remember, Darwin understood or said that evolution was a slow, gradual process. And that's why he needed the geologists and their evidence of an old Earth to support his theory, right? He needed the Earth to be very, very old because he said this whole process of evolution by natural selection is a very slow process. So when he looked at the Cambrian explosion, and a little bit later on when Darwin looked at the evolution of flowering plants, he said kind of the same thing. He was very distraught or bothered by the fact that it looked like these species arose very quickly. Darwin's idea of evolution by natural selection in terms of the pace at which it occurs at that time was something called gradualism, right? So gradually species change through time. Now, so that we don't get confused, I want you to understand something about gradualism. Evolution by gradualism does occur, right? Darwin wasn't wrong on that. Darwin was correct that some species we can show through the fossil record have gradually changed through time. The horse is one of them. If you look at horse evolution, it's little tiny changes through time. But what Darwin didn't know was that there's another speed to evolution. Okay, let me flip over to the next slide and you'll see what I'm talking about. So on the left-hand side is gradualism. So we have this one species at the bottom, and through time it gradually evolves into what we have two species at the top now, right? The other pace of evolution that Darwin wasn't familiar with is called punctuated equilibrium. And what punctuated equilibrium results in is something called cladogenesis. Cladogenesis literally means genesis, to create, the creation of new species. Cladogenesis, instead of being sort of like in the gradualism where they kind of go off on a V, cladogenesis works like that branched bush that we were talking about at the beginning of this part of the lecture, right? Where you coming along and all of a sudden you get all these species that come out, basically it seems at one time. Punctuated equilibrium explains quite a bit about the change of organisms we've seen on Earth. And for one thing, it explains the Cambrian explosion. It explains why in a relatively short period of time, again 20 million years, but still, we get all of these species. That wouldn't have happened through gradualism. That had to happen through another pace, through punctuated equilibrium. So you see what happens in punctuated equilibrium. You got this bird down here, and it moves forward in time. And maybe it gradually is evolving through time, but then some environmental condition occurs, and boom, we get another species. And that species moves on about its business. This guy continues to remain, and he gives rise to another species. So at the end, we end up with 3 species where we start off with 1 in a branching way. And this can happen relatively quick, right? So you see time, get rid of my scribbling. You see time here? We're saying that the branches that occur, so this is gradual change through time. This is very quick change through time. This type of speciation is called punctuated equilibrium for a reason. Let me get a blank screen because I want to draw some stuff out here for you to show you how this works. All right. Let's take a graph and put time on the x-axis. And on the y-axis, let's put evolutionary change. Right? Speciation, new species being formed. Something like that, some degree of, some measurement of evolutionary change. Here's what punctuated equilibrium says. Think about the phrase, punctuated equilibrium. Let's go with the equilibrium part first. Equilibrium means things are at even keel, right? Okay, you learned about that in Bio 1, homeostasis. So the equilibrium part of punctuated equilibrium says, if we go back through a species lineage, that through long periods of time, there's little or no change. So on the y-axis of change, as I move up the y-axis, that's going to be more change. So since the line is parallel to the x-axis to time, I'm indicating no change has occurred. Now, maybe a little bit of gradual change has occurred, maybe a little bit of speciation, but for the most part, the species has stayed pretty much the same. Those periods of equilibrium are interspersed or punctuated with periods of very rapid change, like a stair-step kind of thing. All right? So punctuated equilibrium. Species stay the same for long periods of time, and then a cladogenesis event or species arise over a relatively short period of time. And then they settle down for a long period of time of gradual or no change, and then some periods of rapid change. Now, this whole mechanism or this whole different pace of evolution wasn't really known until early 70s. 1972 is when a group of scientists came up with this idea. This whole idea that evolution can occur gradually, and then there can be periods where there's rapid evolution that can occur. Now, this explains a lot of things. It does help explain the fossil record during the Cambrian explosion. How did we get all those species all at once? Well, during that time, the environment was changing rather rapidly, relatively speaking, and so species that were surviving, because so many of them went extinct now, species that surviving had to change very rapidly to keep up with the environment. Another thing that punctuated equilibrium helps us understand is what happens to these things we call transitional fossil forms. All right? As we move our way through our discussion as we move off this chapter, folks, let me get back onto the chapter, we're going to be talking about different groups of organisms. We'll talk about different plants, and we'll talk about different animals. And specifically, when we get into the animals, we'll be talking about things, how different groups of animals evolved. And one of the questions that's always been on everybody's mind is, where did the birds come from? Birds are an interesting creature. As a matter of fact, your book right now has adopted the new view about what birds are. They're calling them reptiles. Birds are reptiles, folks. Years ago, when I used to teach this class, when we got into the animals, we talked about the fish, we talked about mammals, we talked about birds, and we talked about reptiles. We talked about them separate things. But birds are nothing more than a very specialized reptile. Okay? Birds evolved from reptilian ancestors. You might have even heard sometimes people say birds are the only living descendants of dinosaurs, or the cousin of the dinosaurs. All right, so let's take a look at how these transitional forms and punctuated equilibrium goes together. So here's a dinosaur. Now, I don't know off the top of my head if this is a dinosaur that birds evolved from. It doesn't matter. It's a dinosaur, and this is a modern bird. If modern birds evolved from dinosaurs, okay, somewhere in the fossil record, there should be an organism that is part reptile, part dinosaur, right, and part bird-like. Correct? There should be. Punctuated equilibrium says that species change can occur rather rapidly. It doesn't mean you could do it overnight. It's not like dinosaurs went to sleep one night, Dinosaurs slept. Anyway, and they woke up and some of them were birds. Didn't happen that way, right? Through time, some part of the dinosaur lineage branched off and eventually became the birds. So there should be these transitional forms. And for many years, this was used as an argument against Darwin's evolution, because we had the evidence to suggest that birds evolved from dinosaurs and reptiles, but we didn't have these transitional forms. So people were saying, well, if you don't have the transitional forms, it must be separate creation. Blah, 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 blah. We roll all the way back to Aristotle again. Okay? We roll back to Aristotle again with the rungs on the ladder, and there's nothing in between. But that's begun to change. One of the very first fossils that we found, transitional wise, for this bird dinosaur question, was the fossil of an organism called Archaeopteryx. And we'll talk about Archaeopteryx more when we get into birds, but this is what we think Archaeopteryx looked like. Archaeopteryx was not a flightless bird, but it didn't fly the way that picture in the seagull does. It maybe flew like a chicken does, right? It hopped, and then maybe it flapped its wings to get up, say, perching on this branch that you see there. Archaeopteryx had a lot of characteristics similar to reptiles. For example, Archaeopteryx had teeth. Modern birds don't have teeth. The tail of the Archaeopteryx was very similar to the tail that we find in reptiles. The claws and the nails were very reptilian-like. Even today, folks, if you look at a modern bird, you can see remnants of its reptilian past. Does anybody know what I'm talking about? What part of a bird kind of hints at it being at its reptilian ancestry? See how closely you guys have observed any birds in the past. While you guys do that, I'm going to find you a picture. Oh no, not. I'm going to. Here we go. That's not a bad picture. I'm gonna put this in the chat box. Look on that. Look at that bird. Look at the legs of that bird. That's a bird, right? That's a bird's claw. You guys seeing that picture? You able to navigate to that? Are you guys able to see that picture? Are you able to click on that link? You see what that bird has got on its feet? What do those look like? Thank you, Ace. They look like scales, don't they? Who else has scales on them? I know fish do. What other critter has scales? Snakes have scales. Lizards have scales. Reptiles have scales. See, even today in modern birds, we see some evidence of their reptilian past, don't we? They got scaly legs. All right, so we are now beginning to find these transitional fossil forms to make this link. Archaeopteryx is only one. When we get into the birds, there are several reptilian bird intermediaries that we're going to talk about. Okay, now, how does punctuated equilibrium explain the absence or the scarcity of transitional fossils? Like, for example, Archaeopteryx, I think they've only found, I don't know how many it is, but only a handful of these fossils. Now, let me go back to a blank screen again, and I'll show you how this all fits together. Here we go. So again, got time, change, and we're doing this. Okay. Let's go dinosaur, bird. All right, I'm making it very simple here. So what we're saying is here, this would be the length of time that dinosaurs were alive and died and formed fossils. This would be the length of time that modern birds were alive and died and left fossils, okay? The time in between here would be the time in which those transitional forms were around, the Archaeopteryx. So years ago, the argument was that Darwin's theory of evolution has got a big hole in it because you can't find, there is no fossil of a part bird, part reptile. Well, indeed, we found them, okay? I just showed it to you. So it's not a matter of whether they exist or not, they do. The question is, why are they so rare? All right, well, punctuated equilibrium says that for, I don't know, millions and millions of years, you got dinosaurs living and dying and making fossils, okay? For millions and millions and millions and tens of millions of years, you got birds living and dying and making fossils. But in this really short period of time, during this part when it's being punctuated, that might only be, say, 1 million years. Okay, well, play the game of quantity, right? If the dinosaurs were around 250 million years, modern birds have been around, oh God, 65 million years, and let's say that those transitional forms, the Archaeopteryx and all the other ones we're going to talk about, they were only around, say, oh, I don't know, and I'm just making this number up, let's say 2 million years. Now, who's going to leave behind more fossils? The dinosaurs and the birds that were around collectively, what, over 300 million years? Or the transitional forms that were only around a couple of million years? Who's going to leave behind more fossils? In other words, who's going to have a larger population in the amount of time that's going to die and then eventually leave fossils? Would it be the dinosaurs and the birds or the transitional ones? Yeah. So the absence of transitional fossil forms really is kind of a misnomer. It wasn't an absence. It was a scarcity of transitional fossil forms, right? So prior to being able to fill in these gaps, the argument against evolution was unfounded. And when we fully understand how punctuated equilibrium works, we understood that indeed those transitional forms are there. It's just that during the time when those transitional forms were alive, the Archaeopteryx, they didn't live very long. There weren't many of them. Very quickly, the next group of organisms took over, in this case, the birds. And since you have 300 million years of birds and dinosaur reptiles and only a couple of million years of Archaeopteryx fossils, remember, fossils are kind of rare. They're not easy to find. How many of y'all have ever found a fossil? Walk around outside and went, oh my God, look, a fossil. I haven't, and I've been looking for fossils all my life. Now, there are certain places you find them much more readily than others, but they're not very common. So if dinosaur fossils are not very common, and there were a boatload of dinosaurs around in that 250 million years, and bird fossils, you know, they're not the easiest thing in the world to find. You can imagine that those transitional ones that were only around for a couple million years and left behind very few, they're much more rare to find. I was so excited when I went to the American Museum of History in New York years ago. If you ever go there, go to the top floor of the museum. That's where all the dinosaur fossils are. And I walked in and I could see across the room, it was Archaeopteryx. I'm like, oh my God, I'm going to actually go see an Archaeopteryx fossil, right? And for a nerd like me, that's incredible. So I go running over there and I'm looking at it and I'm like, oh my God, it's incredible. And then I look up in the upper plaque and it says, oh, this is actually a plaster cast of the Archaeopteryx fossil. It's not a real one. I'm like, oh man, I was so disappointed. There's not very many of them around, so the folks who have them keep. I don't know how many they've found. They've found a lot more now, but they haven't found a lot of them. They're relatively rare. All righty, folks. Any questions on any of that? All right, so understand, just so I make sure we don't make a mistake, gradualism and punctuated equilibrium are two paces of evolution. They both occur. But the punctuated equilibrium one explains how we get these rapid development of species. All righty, folks, that's all I have for today. If you have any questions, by all means, please stick around. I will post the recording that I do have. I'll have to make myself a little notice to let everybody know that I didn't get the first half of it, unfortunately. That was my fault. So anyway, y'all have a good weekend. I will see you next Monday. Again, check the field, check your Blackboard if you want to go on those field trips. Shoot me off an email. You can do it anytime. It doesn't matter when you RSVP. You can do it anytime. Let me know if you want to go. Okay? All righty, folks. That's it. We'll do chapter 25 when we get together next Monday. We're also doing lab number 2. So make sure you have that lab set up. Or have that lab brought with you. All righty, folks. Have a good evening. I'll talk to you later. You too, Ace. You have a nice weekend.